You imagine, that's a song by John Lennon. Imagine, important song. You imagine it's a very special time for me, very special. But this time full of thankfulness. Not the last, not the least, because look at this room. It's impressive. Yes, okay. We'll tell you about science. First, we will start with an introduction. Then, we will speak about my first catastrophe. Then, my success. Then, something undecided. Voilà, Edward Kallenberg, Sir John Kendrew, Ted told already about this person, ein Doktorvater, wie man sagt. And, well, he taught me science and a lot about social responsibility. This one hired me for a strange project, a project which was very open to we don't know where, and it was dealing with water in the electron microscope. And he gave these young scientists that he appointed, he gave them an incredible, a total freedom. You have 5 years, be great and do something great. Okay, that's a good program. Why cryo-EM? Because of water. An electron microscope must work under vacuum, and water evaporates in the vacuum of the microscope, so it has to go. My electron microscopist has worked a lot to deal with this absence of water. Of course, every molecule floating in water, if you remove water, they aggregates. And if you are good in specimen preparation, you have fine aggregates. If you are bad, you have coarse aggregates, but aggregates you have because fish never fly. So, our story, also even tough particle like a bacteriophage, T4, if you're just drying on a support, they collapse horribly, like that. So, electron microscopist has been smart, and they have invented method. The most well-known is negative staining. You dry the specimen in presence of the salt, and the salt concentrate with the water going, and at the end you have a kind of scaffold of heavy salt around the specimen. Other people try freezing. You first freeze the sample and you remove the water, not from the liquid phase, but from the solid phase. That's not bad, but you can see, nevertheless, the shape of this head is not quite kosher. My hero of that time, but still now, and I really think that he should have got the Nobel Prize with us, is Nigel Unwin, and he is an incredibly imaginative guy, and in fact we were working very closely together, not physically, but in the mind. And in fact, the first time I went to Cambridge, I was invited in his home, and he put me to sleep in his guest room, and under the bed was a telescope, a 15-centimeter telescope, just like the one I've built myself when I had about the same age he was. So Nigel had a good idea. He thought, the problem with negative staining is the stain. It's not good for a virus to be in heavy metal salt. We should put it in something else. He had a lot of ideas, but the famous idea was replacing heavy metal salt by sugar, because sugar is much more sympathetic for the biological material. And so he joined his force with Richard Henderson, Well, alors this one got the Nobel Prize, and they get in 1975 the first molecular structure of a protein, the rhodopsin, voila, the little bug that you find in the Allobacterium halobium, voila. And this, another very important person was Bob Glaser, and he, 1975 and 76, he was trying to play with ice and trying to keep the water, the ice in the specimen, and he published this photograph, and this photograph was, wow, was very impressive. And you see, this is cell envelope, very much broken. It's embedded in ice. Here you do not see in detail, but the structure tells that this is a sheet, a thin film of ice. And you see this envelope structure here. They are beautiful. And at that time, I was just trying to find how to preserve them without water, and by salt or by sugar or by any kind of things. And so I thought, oh, this is the future. And so I was appointed at Yambel 78 with this project, how to deal with water in the electron microscope, and the project started very badly. In fact, I was still in Basel and prepared to go for Heidelberg, when a rumor went around saying that in Munich, a group of Frau Dr. Dietrich had developed an electron microscope working at 4 Kelvin. And in this machine, in this apparatus, the beam damage was very much reduced. Because beam damage, voila, is the second big problem of electron microscope. The chemical bound, typically this is 4 electron volts or so. An electron, the kind of electron we use, is 100,000 electron volt. So really, electrons are not good for chemistry. And we had to deal with this beam damage problem. This is a fundamental limitation of the electron microscope, and a good idea could be at very low temperature. Perhaps damage are reduced. And that's exactly what the people in Munich were saying. I was at that time, during my PhD, I worked a lot about beam damage, and the method we used, developed following the step of Bob Glaser, was by electron diffraction. So we have a crystal, and we irradiate the crystal at low dose until the spot fades away. And so we can measure the dose which produced the damage. You cannot do that with an image, because the time you take the image, the specimen is already gone. But by electron diffraction, it's okay. And so this is the kind of thing we did. And so I phoned Erwin Knappek, the guy of Munich, and I told him, oh, you have an extraordinary microscope. I know how to measure. Together we are going to publish something formidable. So we worked together, and soon we had this kind of results. Don't be too much impressed by the fact that there are much more points. There is much more points just because at very low temperature, atoms are less shaky. Therefore, you get more, not information, yes, more information. But what is important is how it fades away. You remember, with 1.6 electron per square angstrom, everything is gone. Here we are at 22 electron per square angstrom, and it is still here. Wow! What do you do with that? You publish. And so, beam damage to organic material is considerably reduced in cryoelectron microscopy. Gain a factor 30 to 300. It's written here. Gain, yes, 30 to 300. And of course, with this, it was easy to go to my boss and to tell him we should buy the lens and have it installed and ready to work with this method at EMBL. Great. It took 2 years to have the lens prepared and to have installed in the, well, the group of EM development, material development, have prepared an electron microscope to receive the lens. They did a perfect work. Therefore, within 1 week after the lens was brought to Heidelberg, it was installed in the microscope. With Jean Le Paul, who came in the meantime, we were also very well prepared. Within a few days after the lens was installed and we knew how to work with it, we discovered that we were not able to repeat the result. But not at all a catastrophe. Beam damage at 4 Kelvin is, oh, you are laughing. There is nothing to laugh about that. Yeah. 4 Kelvin, no, not even better than room temperature. And a lot of trouble because at this temperature, charge effect and thermal effect are more severe. A catastrophe. What do you do with that? You go to the boss and you tell him, sorry, it doesn't work. And the boss tells you, be sure of it and let it know. So that's what we did. And voila, that's my shortest paper, 15 lines, most expensive paper. Sorry, it doesn't work. Then we organized big experimental effort with all those who has been involved in this 4 Kelvin attempt. There were about 10 groups who were, and most did agree with us. Huh? That's a problem. And so we had to organize a kind of control experiment, a complicated operation, because the experiment is complicated, this beam damage experiment. And so everybody was involved, international study group. And for the first time, I came in Nature. The Siemens group has agreed with the group at Dubochet group at EMBL that the protection gained by working at 4 Kelvin compared with room temperature is not more than tenfold, and tenfold is very optimistic indeed. Oh la la. So, explanation. Standard explanation, you know, it's a very complicated experiment. There are plenty of possibility to make an error. We had our favor explanation. At that temperature, we were working by electron diffraction. This means you don't have an image. You have an electron diffractogram. You do not see where you are on the specimen. And at that temperature, the electrical conductivity makes that the specimen has a very strong tendency to drift. So you have the beam and the specimen gently drifting under the beam, so that it's always a new specimen that is under the beam, and it is therefore, it appears to be very, very resistant. Nice explanation, but that's not sufficient. So, 35 years after, at the end of last year, Erwin Canopic, that I didn't saw since that time, phoned to me to let me know that Madame Dietrich died recently. And we started discussing, and we found ourselves in very good friendship. Therefore, I was in his lab, in his home, some months ago, and together we wrote again the story of this catastrophe. And we came to the conclusion that they were two young scientists who had every reason to love the word dramatic cryoprotection factor, and considerable reduction of beam damage. But their drive to success, ambition, and pride clouded their scientific judgment. They strayed off the ridge, but they were lucky to be able to identify the error and retrace their steps. In the following years, they had the opportunity to be successful in different ways. Not everyone will be so lucky. You are all scientists. Be careful. Yes, this is Erwin Canopic. He left Siemens and he became major of his little town. And he was 12 years long major. And his little town is a zero CO2 town, thanks to geothermy. Yes, he did that. It's an example, a remarkable example for Germany and for Europe. He is now president of the Geothermy Verband of Germany. Bravo. Voilà. And for me, in the meantime, while we were waiting for the electron, the cryo lens, we were working and learning how to deal with water in the electron microscope. And the problem, of course, with freezing water is ice, and ice is not quite like the liquid. So we were trying to freeze correctly the water so that it makes as little problem as possible. We had this sophisticated system. This sophisticated system. You have here the grid, which the specimen holder. You have here liquid nitrogen. You have a nebulizer sending throw microdroplet here through, and you let it fall down. It catch a few droplets, and it frees the droplets immediately. So that was then where you put the specimen in the specimen holder here, and you have here liquid nitrogen well protected to do that, and to keep the cold. And so you had a droplet. This is a typical nice droplet of water. Ice, characteristic sign of ice. That's good. And once Alistair McDowell, my colleague, decided to make a minor modification. He put here a small beaker, and he filled this beaker with liquid ethane. And then he did the same experiment, and he got that. He called me to the microscope, and we looked at that, and we thought, oh, what is this? And we thought first, boy, it must be liquid ethane, a drop of liquid ethane. No, it can't be. We know liquid ethane. It should evaporate at that temperature. So what do? We stop the cooling device, and we let the specimen slowly warm in the microscope, thinking that at some moment it will evaporate, and it will tell us a little bit about what it is. At minus 135, suddenly in 1 second, the drop transformed into a polycrystalline that we knew perfectly well. This was liquid. This was cubic ice. Cubic ice that we knew and that we could demonstrate to be identified by electron diffraction. It was cubic ice. Cubic ice is very similar to normal ice, but it is, well, there are plenty of forms of ice, but this is one of the classical forms of ice. And if you have some material which is amorphous, and which turn into ice when you warm, it must have been vitreous water. Ha. So we had vitreous water. And I said to Alistair, oh, we have something great. He remembered very well the sentence, and I remember very well the moment. And voila, Alistair McDowell, this great guy. We were together the day before yesterday. This is Sir John Kendrew. small story. I show this photograph since 20 years. And, and the day before yesterday in Heidelberg, show it again. And then after, people laugh as usual. And after that, a philosopher of science of United States came to me and told me, oh, there is a naked woman. Bon, okay. Voila, Lester. Ah, yes. So we decide we remove the other photograph and we have this one. Voila, and this was a very fundamental moment, and in fact, the Nobel Prize is because of that. The trouble with water, with vitreous water, is that vitrification should be impossible. Yes, that is interesting, and the reason why you mentioned a few words on that is this guy. This guy is Basile Luyet, Basile Luyet is from Savièse. He is a priest, a Catholic priest from a very severe congregation, and he spent all his life trying to vitrify living material. And he came with the idea of vitrification. He noticed that he never succeeded, and together with a very excellent student of a co-worker, he could demonstrate that vitrification must be impossible for thermodynamic reasons. And don't laugh from thermodynamics. It's a very solid science. And by the way, he's from Savièse, and those who, a number of know that we have a little chalet just here. Yeah, that's amazing. And at school, I start school in a village which is about here on the other side of the valley. Okay, now why is it impossible? I give you just one rapid explanation. We have the phase diagram of water. Vapor, liquid, ice. Triple point. And if we warm water at 100 degrees at normal pressure, when it arrives to 100 degrees, it boils. No, that's not true. It's ready to be boiling. But you may continue a while. You may continue a little bit, and suddenly it will start boiling. This situation is classical in thermodynamics, and it will continue until it becomes impossible. This is what is called a spinodal limit, and when you can't reach the spinodal, it's finished. You can't go anywhere. The liquid state doesn't exist anymore. You can do what you want, it's impossible. And then at low temperature, there is all the sign that you have a similar situation. And what happens when you approach a spinodal limit, every parameter becomes crazy. For example, you take the density of water. Maximum at 4 Kelvin, at 4 degrees centigrade here. And when you cool, and you see the density seems to collapse. And so you say something get wrong. And you can take any other parameter, they are getting completely crazy when you approach -30, -40. And so people understood that there is this spinodal. There are other more theoretical reasons. No, we have not time to go into that, but it's clear that at -40 or 45, the liquid state can't exist anymore. So what do we have? Nobody knows. So the first consequence was that that we send our result to nature, and we get this beautiful answer. You can't bend nature. Good joke. And they were wrong for two reasons. The first one, we can't vitrify. No problem. It's easy. It's rapid. No problem. Oh. The second is at that moment, when they wrote that to us, they had in press in the journal a paper by Bruggeler and Meyer, who obtain exactly the same by a different method, and they test by X-ray diffraction the presence of vitreous water. So this group here, in 1980, had proven, had in press in Nature, the proof that vitrification was possible when the Nature was refusing it. Okay, so we continue to work on our little ice things, and Patrick Eschlin, the director of Journal of Microscopy, after some time told him, but you must publish your vitrification story. So that's what we did, and we published this one, which is the paper you are referring, the small paper here. And voila. More about strange waters, what shall we do? Yes. So, first conclusion. Vitreous water is not what we believe it is. It's not just liquid water which in some way is immobilized. It's something different. But nobody knows what it is. And even now, we understand very little. These two phases of vitreous water, and it could be another seminar on what is known about that and why we don't understand what is going on with this strange substance, which is liquid water, which is much more complicated than that what we are able to deal with. But it doesn't matter. For a virus or protein, when it is in vitreous ice, it shows all the signs that it is perfectly happy. Therefore, apparently there is no sign of a problem that the fact of immobilizing the specimen in this thin layer of water disturb it in any way. So we believe we have a faithful representation of biological objects when they are vitrified. Now the second aha takes place like that. You have the biological material, the suspension, and you want to spread it on a supporting film very thin, of course, because anything more than 1/10 of a micron thickness is not good for the electron microscope. And it's difficult to spread water, because water likes to minimize the surface tension. A drop of water is a sphere. And if you want to stretch it on a very thin film, you have to make that the interaction, the interaction energy between the supporting film and the water is exactly the same number than the surface tension of the water. And you have too big number that you have to adjust. It's very difficult. And we were trying to learn about this arrangement of the supporting film so that water can nicely spread on it. But my colleague, Marc Adrian, he died in 2013, shortly after his retirement. He worked here all the time. He was here with us in our lab here at the Law. But he is very stubborn. And he didn't like this spreading story. So he wanted to do it without support. And our grids, AM grids, are made of holes, 18 micrometer. And so he wanted to spread the grid through the holes. But this means having a thin layer of water, which is 200 times thinner than broad. Crazy! That's in terms of energy, it's impossible, but he did it. And it worked. And he got this kind of thing. You see, this is a thin layer of semlichiphorus virus floating in a very nice thin layer of pure water, just gentle water, good water, immobilized, of course. And of course, here you can imagine here, yes, that's the method. You put the drop on the grid, you remove most of it with the blotting paper, and in 1 second, the drop is gone in the blotting paper, but the last 1/10 of a micron take 1 more second to go away, which leaves you all the time to let the grid fall down in liquid ethane, and the 1/10 of a micron thick layer is vitrified that way. Of course, the 1/10 of a micron thick layer, when you put it at -180, it freezes very rapidly. It doesn't freeze, it vitrifies. Okay, so this was a great time, you can imagine. You had all the people of the water coming in the lab because they wanted to see this impossible thing, and it was easy to see. And so we really learned about water at that time with all this real water professional coming and teaching us about water. Then we had also all the people who wanted to have their sample, observing it. So we had the course, the first cryo-EM course. We had Nigel Unwin coming to see as you said, to see the thing. It was a great. And one morning, very, very early, I got a phone call from Pierre Genest. Pierre Genest is the guy who got the Nobel Prize by studying how water spread on a surface and how polymer mixed, how DNA mixed with DNA. And he was teasing me and he said, "Oh, I know that you don't know why your very thin film is stable or pseudo-stable." "Oh, no, I don't know." "Oh, I tell you. And the reason is very simple. You have two surfaces, very close surface, and in order to break the film, if the film is broken, it disappears immediately, 10 - 6 seconds to go away. But in order to start breaking, you have to fuse the top and the bottom surface. And this is something very difficult. How does it happen? Oh, Dejean told me, I know. It will take about 1 million times longer. So about 1 second. That's okay. Yes. Bon, so we had that. At that time we had big problem with, a bit before we had big problem with the second boss of AMBL, Leonard Phillips. He thought that it was over, the time for physicists in biology was over. Now we need medical doctors. So he didn't like us very much. And but when we had get this nice photograph, and this is the virus with which adenovirus, this was his pet virus, and so we became good friends again. And so now you see, you have a number of viruses perfectly well preserved. Well, there are a bit of beam damage, but that's, so you have to put not too much dose. But this is the same virus in all orientation. Now you have the information to make a 3D reconstruction. And that's what we did. And well, there are a little bit of tricks here. And we got the first 3D reconstruction from a virus in liquid, in vitreous water. And this here, this was 1968. No, 86, sorry. 86, and the resolution was 35 angstrom. 35 angstrom. Okay, so the people of X-ray said, well, it's very nice, this is blobology, blobology. And, but then some people worked hard, or we did also, but others worked very hard. This is Joachim Frank, this is Richard Henderson. Joachim Frank in particular developed all the mathematics for and his program for his software for treating the data. Richard Henderson, I always say, he invented nothing. But he flew over all the things. He's the youngest of three, but he is the I would say, the most wise guru of cryo-EM. And now they are nearly routinely at 3.5 angstrom. This means the resolution is 10 times better, which means that the volume that you resolve is 1,000 times smaller. So in 35 years, we gain a factor 1,000 in information density. Whew. That's really Nobel Prize worth. And so you get 3.5 angstrom, and at 3.5 angstrom there is something very special that happens at 3.5, not at 5, not at 2. At 3.5 you see the atoms. And when you see the atoms, you are a chemist. And that's the reason why we got the Nobel Prize in Chemistry. 3 physicists working in biology, all 3 being not in chemistry, get this Nobel Prize in Chemistry. So this proves that the Pater principle is correct. With time, everyone grow to his level of incompetence. Or perhaps it is because science there is a unity of science. And even if you are a physicist, or even if you are a biologist, you may contribute in a strange field which is called chemistry. Voila, so voila, now they get this kind of thing, and now every month really, voila, this is the last, this was I think in the last issue of Nature, yes, or 2 weeks ago. And well, here there are a lot of people working in DNA, in DNA, well, polymerase 2 action in pre-initiation complex. That's a pre-initiation complex. And you see, the resolution, you do not see every atom, but you see all the helices. You can follow the chain. You can, in the favorable case, here the resolution is something like 4.5 to 6 angstrom. You cannot, there are only some favorable case where you can determine the side chain of the amino acid, but since for all these proteins which are here, you have the X-ray data, you have or not all, but most, since you have the computer simulation with the sequence a little bit, you really, from here, get an atomic map of the transcription complex. And typically, they get ribosomes. A ribosome is 300,000 atoms. And you get as many inhabitants in the whole region or in the whole canton of Geneva, and they put every atom in position. And nowadays, it takes, when the specimen, when the juice is clean, well prepared, and this is the most difficult part. Then when everything is going well, in days, they have the data in the electron microscope, and then the computer take that, and in weeks, they have the atomic resolution of a big complex without need for crystallization. And that's the reason why it changed massively the biology. It will have an importance, considerable importance in biology. You may remember in 1950 and something, and please you remember, when Watson and Crick got the structure of the DNA. From the structure, they understood how DNA can replicate. And then it was thought, okay, we just have to study now proteins, and when we will have the structure of the protein, we will know how it works. It didn't work like that. No, it was much more complicated. But now a lot of people think, now we are so far. We are able to see well enough the structure in the complex state and in different situations, and then we are going to be able to repeat the story of the DNA with whatever you like. That's a bit optimistic, but that's the mood of the moment. Voilà, I think I will stop here, yes. And this is another story. This would have been the third part. The thing that we continue also here in Lausanne to deal with thick specimen, and it's not finished. Nobody knows how, if we will be able to make finally a molecular map of a cell. It's an ongoing work. I will not speak about it now, and I thank you for your attention.